Hello scholars, welcome. Mr. Hinkle here. Today we are talking about fossils, the remains of once living organisms preserved in the stratigraphic rock record. Let's get into it. So our specific objective is to discuss what are fossils, why they are important, how they form, and then what we use fossils for currently. So as mentioned, fossils are the remains of once living organisms. They're preserved by natural causes, sedimentation, in rocks in the Earth's crust. And the study of fossils, or the study of life that existed prior to the Holocene epoch, a specific time period in geologic history, is called Paleontology. This prefix, paleo, meaning ancient or old. So we got a variety of uses for why fossils are important. Well, they give us the history of life on Earth. They're windows into what life was like in geologic past. They provide evidence of past environments and climate. We would call this paleoclimate and depositional environments. They show us evolutionary processes, evolution being how species change through time, and the diversification that comes with how species change through time. They give insights into plate tectonic movement. We could really look towards one of Alfred Wegener's 4 lines of evidence for continental drift, the location of fossils across different continents. Fossils help us to date rocks relatively through fossil assemblages. They indicate extinction events, the 5 major mass extinctions within the last, since the beginning of the Cambrian. And then they also help provide insight into human evolution over the last 7 million years. So in order to become a fossil, there are 3 main occurrences that need to happen. Well, first off, there has to be a part of the organism that is able to be preserved. And the most likely parts are going to be hard parts of organisms, bones and teeth. Not exclusive, but they're the most easily preserved. Preservable parts must be buried, and it's a rapid burial, by sediments. Fossils exist in sedimentary rocks. Before sedimentary rocks are lithified into a rock, they are accumulations of sediment, and when preservable parts make their way into accumulations of sediment, they then have the opportunity to become fossilized for you and I to discover today. They also need to escape destruction. And that can be physical, it can be chemical, it can be, what else do I have? Biological. In order to be preserved, they have to have parts that are preservable, rapid burial, and escape destruction. So here are the ingredients for how we make a fossil. The types of fossils that we commonly see. We've got 3 main types here. Body fossils. This is going to be the direct organism. Its shell, its bones, its teeth, its preservable parts. It is the actual organism through some mode of preservation that is preserved in the rock record. Now, sometimes we only see traces of fossils, burrows or feces or prints that are left behind, which are still very informative into what was happening in Earth's past, but it's not the exact organism in and of itself. And then last but not least, we've got microfossils, micro going to microscopic organisms, and the remains that these microscopic organisms are going to leave, often seen when we discover them using some sort of a microscope. Okay, cool. So how do fossils become fossils? We've got the requirements, the types, and now we're into modes of preservation, which I'm running out of space here, but it's okay because I have an eraser. So preservation is the next thing that we're getting into. Common modes, per mineralization. This is where the pore space in, say, like a tree, the pore space between the cells gets filled in with mineral deposits, solidifying, thereby preserving that tree or species or whatever it is into the rock record. So you have minerals essentially filling in the pore spaces of the body, preserving it. Carbonization, this one's often seen with leaves or organic material, where the preservation through the compression of sediments leaves a carbon imprint. We've got molds and casts, organisms imprint in sediment, later forming, filling in. So the mold is the hollowing out of a space, and then the cast is the filling in. When you go to a natural history museum, sometimes you see the actual fossils, but often you will see a mold and a cast. They can withstand the elements a little bit better, especially if it's an important fossil that we want to preserve for scientific study. Last but not least, amber preservation. The plot to Jurassic Park is that mosquitoes that were feeding off of dinosaurs were preserved in amber, and those mosquitoes held the DNA to the dinosaurs, which then could be brought back to life. It's a fun idea, rooted in some science, that the mosquitoes from Earth's history were preserved and fossilized in order that we could study them today. So this is not an exhaustive list, but this is a good introductory list for you. Fossils tell us the history of life on Earth. And there are key moments in Earth history, like when life decided to crawl out of the ocean, when a fish decided to walk on land. That is a gross oversimplification, but there is a transitionary fossil, Tiktaalik, which is the first vertebrate. Here's the fossil, here's the recreation. The first vertebrate to evolve 4 limbs and crawl onto dry land. The first tetrapod, terrestrial tetrapod. Very important. The Archaeopteryx is a transitionary fossil. It's basically a dinosaur with feathers, indicating the evolutionary adaptation for when species developed the ability to fly. So fossils, there's a lot of fossils that show the history of life. There are some key fossils that are called transition fossils. Let's put it up here. That show us key evolutionary jumps in the history of the Earth. As far as evolution goes, we have diversification. We also have mass extinctions. As evidenced, the reason we know this is because of fossils. Fossils correlate with rock layers, stratigraphy, and when we see a sudden absence of 50% or more of the species preserved in the rock record, then that's an indication that a mass extinction had occurred, and we can pair those with geologic events from Earth's history to gain an understanding of what happened in the history of the Earth. And our understanding outside of the scope of this lecture is that there have been 5 major mass extinctions indicated by their fossil signatures. So let's talk about stratigraphy. We're just kind of hitting all the big topics here. This is evolution. Oh yeah. Stratigraphy. Oh yeah. Currently, we have fancy equipment, mass spectrometers, that allow us to understand the radioactive decay of elements that are in various rock layers. Well, it wasn't always the case. Before that, before we could put exact age dates on rocks, we were looking at rocks in the relative ages. Is this rock older than this rock? Is this rock older than this rock? To understand the history of the Earth. And fossils, fossil assemblages, were really important for showing that. We could see that this cluster of fossils is always younger than this cluster of fossils. And there are specific fossils that identify narrow geologic ranges, and we call these index fossils. Very important for understanding the relative ages of sedimentary rocks. Now, this use of fossils to establish relative ages is called biostratigraphy. In stratigraphic correlation, you can use the fossils, you can use the rocks, you can use the time, you can even use the magnetic signature. But when we use the fossils, it is called biostratigraphy. So we'll just add this little highlight in here. Biostratigraphy, giving us relative dates. More on this in my lectures on geologic time. This is kind of a footnote here, but this is a huge, huge topic. Okay? So what do we use fossils for today? Well, we learn the history of the Earth, absolutely. We learn about past climates, which is really important in today's day and age, looking at our current climate and the rates of change of current climate and comparing it to how climate has changed in the past. Climate change is a natural process that has always occurred on Earth. Earth's climate has always been changing. But how has it changed in the past relative to now? How have our impacts accelerated that change? These are scientific questions that fossils can help give clues to. In an age of energy, fossils and microfossils can be indicators to petroleum reservoirs. So we have a comprehensive overview of how much of this finite resource is available. And then maybe you have a fossil collection. If you do, I'd love to see. Send me a photo. Fossil collectors have been around since the first discovery of fossils in the mid-1800s, and people have been using it for recreation alongside science and education since we found out that rocks hold these amazing clues to our Earth's geologic past. In conclusion, fossils are the remains of once living organisms. There are 3 requirements: preservable parts, rapid burial, escaping destruction. They come in 3 different types: body fossils, trace fossils, microfossils. There's different modes of preservation. And fossils tell us about evolution and the stratigraphy of rocks. Thank you so much, and I will see you again.